I'm kind of plugging my course, but it's also a good way of showing off some nice aspects of kind of group theory or algebraic group theory. I don't know the right word to use. It's a nice way to show off how a lot of things interact. So I want to tell you about the Steinberg representation, which is an interesting thing. In the end, I probably won't. I mean, I'm not going to give you a whole ton of proofs. I'm hoping that I give you enough that you can say, "Oh, that's neat," since you're sitting here after pizza. But I need to, probably most of what I will say will be just trying to make sense of the words in the title. So let's start with the first, well actually, I didn't think about what the order, but anyway. The first thing, the order of the words in the title. The first thing I want to talk about is a bit about representations of finite groups. So G, for a little while, G will be a finite group. Later, G will be not a finite group, but for Roman numeral 1, G is a finite group. And E, honestly, E is the field of complex numbers. Or an algebraic closure of the rational field is just as good. Or, so here's the actual honest grossness. If L is a prime number, you can take some completion of this field and then take its algebraic closure. And that's actually what you're forced to do for many of the finite groups that I am interested in by some construction due to Deligne and Lustig using the L-adic cohomology of algebraic varieties. Okay, you can ignore all that. So what it is characteristic 0 and algebraically closed field. But if you like to think it's the field of complex numbers, you're fine. So and yeah, okay. So I want to look at vector space. G's a finite group. Surely I only have to think about finite dimensional vector spaces over this field. Finite dimensional complex vector spaces. And such a vector space, I associate a group, the full group of E linear automorphisms of this group. So that is a fancy way of saying the dim V by dim V invertible matrices with entries in E. So it's a matrix group, and to that matrix group, I would like to put G inside that matrix group, though I don't care whether it's actually injective. I just need a group homomorphism from G to that matrix group. So that's what I mean by representation. And now the annoyingness begins. Some parts of the world refer to representations by rho, and some parts of the world refer to representations by V, and I'm not sure what determines it exactly. Some parts of the mathematical world have different biases. I guess the people that talk about infinite dimensional representations of, say, real Lie groups or something tend to refer to rho. And in finite groups, you tend to talk about V. But maybe for a while, I'll carry around both and say this representation is called rho comma V. So you need to know the space that it acts on, and you need to know how it acts. So rho is telling you how elements of G act on V. You give me an element of G, I apply rho to it and get a matrix. You give me a vector in V, I can do that matrix to it. Yeah. So that is what I mean by a representation. And that is what I will talk about a little bit in the spring, is the theory of such representation. So what's nice about them? Sounds like a lot of stuff. It took me a little while to say. But you may have seen theorems that are of the form, any finite group is a subgroup of something. So I actually tortured my 215 students by proving that any finite group is a subgroup of a matrix group, though I guess I did it of matrices where E was finite instead of E. But you could always put any group inside a matrix group like this. And so you could have not bothered to think about the axioms of a group. You could have just formulated what's true about these collections of invertible matrices and then said, well, my finite groups or any groups are things that are subgroups of those, so closed under multiplication and so on. But there's good reasons for the axiomatics. But it turns out that there's lots of numerical, I don't know how to say it, but numerical stuff that's stored, facts about G that are stored in some convenient way in terms of the representation. So let me tell you a little bit about that. So to a representation, rho V, associate the function, it's just a function, not a homomorphism or anything like that. Function goes from G to E, and I guess I'll call it chi sub, I'll just call it chi. Chi sub rho or v or something. Anyway, this is supposed to be the character attached to this representation by the rule chi of g. Oh, that's just the trace of rho of g. All right, so what's nice about trace? If you give me a matrix, well, you give me an automorphism of v, then maybe I haven't bothered to tell you what basis I have in mind, and maybe you and I work out a basis for v, and we get a different answer, which is fine. There are lots of bases for v. Then you will have different looking matrices than me, because we're writing our matrices with respect to different bases, but the trace will be the same. The trace doesn't care what basis you pick. So somehow this is an invariant sort of construction. This gives me a function. You can say, why would I care about that function? And I want to persuade you that you will, but I won't prove very much. So I'm not sure that I will persuasively argue it. But notice that, e.g., that chi of 1, so even I can work that one out. Chi of 1 is some integer, positive integer, I hope, non-negative integer, depending on how pathological v is. But it is the trace of the identity matrix, which is the dimension of v. Remember something about the representation, the dimension of it. Okay, fair enough. Good. Right. So, theorem. No, not quite theorem. Sorry. I got ahead of myself. Given functions. Slightly ahead of myself. So note 1, chi of 1 is then v. Note 2, that chi is constant on conjugacy classes. Pause. So what does it mean to be a conjugacy class in G? I'll state this here in a second. If H is equal to x, G, x inverse, there's an equation in G. Okay, there's a lot of letters, but G and H and X are elements of G, and I get one from the other by conjugating. Yeah. Then rho of H is rho of X, rho of G, rho of X inverse. So the matrix rho of H is obtained by conjugating the matrix rho of G by some invertible matrix. So the trace of rho of H is the trace of rho of G. So the characters of representations are what's called class functions on G. So they're functions like this that are constant on the conjugacy classes. So the theorem says, in fact, that there's all sorts of words that I have to use. Okay, anyway, that the characters of representations of G span the class functions on G. So that's first version. We'll refine. We'll get better. So I can look at the vector space of all class functions. If I add two class functions, surely I get a class function. I'm sure we get a class function. So I can think about that vector space, and in fact, I even know the dimension of that vector space. It is the number of conjugacy classes, right? Because I can take a function that is constant on one class and 0 in every other class, and surely that gives me, in that way, a range for a basis. And right. So I understand the class doesn't. I'm just saying that while I have no reason to expect that I get out those basis vectors that I was just talking about, the ones that are constant on one class and 0 in all the other classes, those are probably not the character of a representation. There's no reason why they should be. Nevertheless, I get a spanning set. And more precisely, or moreover, the characters of the simple, the simple representations of G form a basis of the space of class functions. So what does simple mean? Right. So where's my representation? I have V, and every element of G acts on V by forming a matrix, and I can move vectors in V around with an element of G. So I say that it's simple if there's no smaller subspace than V, except 0, that is invariant under the action of all elements of G. So V is simple. Here I'm pretty sloppy, not writing rho. How do I say it? If W is contained in V is not 0, and rho G W is contained in W for all G, then W has to be all of G. Yes?
This is maybe just a cultural thing, but is simple the same as irreducible?
It is exactly the same thing as irreducible, and I don't have a good answer for you why you would use one word or the other. But simple is also called irreducible. Right. So if I have an invariant subspace that's not 0, well, the only invariant subspaces of a simple module are 0 and the whole thing. It's just one way of specifying that. And what this says is that if I take the simple representations, they form a basis. So there's a lot of stuff hiding in the background that I'm not telling you. The fact that I'm working with a field of characteristic 0 actually means that every representation can be written as a direct sum, local language. But I can think about it as being consisting of simple pieces bound together in a simple way. So I can take, for example, I could take matrices that, so V would be V1 plus V2 means that the matrix of a vector G, or a group element G, acts by this matrix on V1 and this matrix on V2, and that's always true for every G. So I can arrange that. That's what it means to be a direct sum. And since E has characteristic 0, or more generally, as long as the order of the group G is invertible in the field, which for free in characteristic 0, then I can always arrange that any representation can be written as a sum of semicolons. So that's a nice property, and it makes the representation theory somehow easier. Right. So I get, in fact, a basis for the space of class functions. And even a little bit more, given class functions phi and psi can form phi psi to be 1 over the order of G times the sum, the elements of G of phi, G psi of G bar. And now I'll say, okay, pretend like E is C. Otherwise, you have to invent something that's like complex conjugation, which is easy enough. I'm not annoy you with it. In the examples, the only one that would really cause problems is this. Because I can, of course, embed a copy of the algebraic closure of Q in C, and then I get a complex conjugate. So I want something that's sort of a Hermitian inner product, though. So this gives me a non-degenerate linear and anti-linear inner product in the space of class functions, and in fact, irreducible. So, see, I did it. Symbol. The characters of the simple G representations form an orthonormal basis with respect to this inner product. So that is a nice thing. So now I pause a little bit and say, almost everything that I've said will still be true if I replace finite by compact. So what do I mean by that? Some kind of topological group, and then I insist that this be a continuous representation of G. Almost everything that I've said, the fact that everything is a direct sum of simple representations and being able to build an inner product like this works as long as I replace the sum by what? An integral. So you have to integrate a new compact group, but you get basically the same answer. So that's a nice thing to see. I won't do that in the spring, but maybe I will mumble about it, but probably not more than I just did. But I get in this way an orthonormal basis for the space of class functions. In particular, I get that the number of simple G representations equal to the number of conjugacy classes in G. Why? Well, the simple G representations give me a basis for the space of class functions. On the other hand, I have another basis for the space of class functions consisting of things that are constant on conjugacy classes. So since those bases, well, one of those bases has this number of elements in it, and one of them has this number of elements in it, but bases have the same number of elements in them, so these are equal. So linear algebra gives me this formula that I otherwise have no real way of knowing why it should be true. I mean, it's not a priori obvious to me in any sort of fundamental way why this count should be the same as this count. Note that it's important for this that I am working with an algebraically closed field, because there are, I guess, maybe fewer but also more complicated simple modules if I don't give myself all the eigenvalues that I might want. For example, if some equation doesn't have a solution, I might have some module that should be simple if I extend the scalar to C, but isn't. Right. So I get this count, and that's kind of my propaganda for the fact that representations encode something interesting about the structure of the group that you might otherwise not have guessed. So, okay, questions? There was something else I was supposed to say about representation, but I forgot. Oh, I guess I'm supposed to tell you.
I have this question.
Yes.
How do you define your function between phi and psi? If you replace G with a set of finite compact, how would that?
So what you need to know is that there's a Haar measure on G, because it's unique up to positive constant, I guess. And I think that this should normalize it. So no matter what Haar measure you choose, it will come out okay in the end. And then you take the volume of G, so you need G to be compact to be able to talk about that, and then you replace this sigma by a curly thing. And then I guess I put dg over here, which represents the Haar measure. So, right. Yeah, but there I really do have to take E equals C. So, what I do otherwise. So I guess some examples. The first one would be to take G to be Z mod n, the cyclic group. And then I'll take zeta and E, primitive in root of unity. And then I get for all I equals 0 to n minus 1, I get a rho sub I from G to E units, which is, of course, GL1E. So I guess I'm thinking of V as being E, and one-dimensional representation in this rho sub I sends a generator, 1 plus nz, if you like, to the ith power of this primitive unity. And those are exactly the simple modules. So it's not so surprising, because this is an abelian group, so its conjugacy classes are just its elements. Yeah, conjugacy isn't very interesting in an abelian group, and these are the simple modules. So maybe our simple modules. So there is a way of thinking about them as modules of our same ring. I told myself I wasn't going to use that language. Sorry. Simple representations. So 2 would be to take G to be the symmetric group in n letters, and then I will take V to be e to the n, which I guess I'll think about as e. Fix some basis that I'll call EI, because everybody's favorite standard basis is called EI. And then if I have a sigma, then I can tell you what sigma does, tell you the value rho of sigma by telling you what it does on basis vectors, and it will just permute the basis vectors. And now I can be more explicit about what I mean, or more explicit, and I can give you an example about what I mean by an invariant subspace. Then the vector S E1 plus En in V is fixed by every permutation. Yeah, if I apply sigma to En, I guess maybe what I really mean is rho of sigma. You'd be happier if I wrote rho of sigma here. So the fact of sigma, the value of rho of sigma, is what? It's E1 to the sigma of 1 plus E to the sigma of n, but we all know that that's just a silly thing. I've just written the sum in a different order, so that is again S. Just written the sum in a different order, so it doesn't move, and so W, the E span of S, is invariant subspace. In other words, V is not a simple representation for the symmetric group, but V is W direct sum of W perp, so that's not this inner product. This inner product lives in the space of class functions of G. That's not what I mean, but there's an obvious inner product for which EI dot EJ is delta IJ, and that inner product plays nice with the action of sigma. I'm not going to check that, but if I take the orthogonal complement to W, I get an invariant subspace. And well, this is just linear algebra that a vector space is has this property, and this, yeah. So this one is invariant, and in fact, this is an interesting simple representation of dimension n-1. So the symmetric group has an n-1 dimension whole simple representation. So I don't know how to tell you too much more about it offhand, but it's not that hard to find, but it, yeah, anyway.
So is does it also have a 1 representation?
Say that again?
Does it also have a 1-dimensional representation?
Yeah, this is a 1-dimensional representation. So every group actually has a 1-dimensional representation on which it acts trivially, like this, right? I apply any sigma to this vector S and it doesn't move. So that is called the 1-dimensional representation. Maybe I should have written that down in the question. 3, because I will use it a lot in just a minute. So 3 is for any G, I can view E as a 1-dimensional representation of G on which each G in G acts as the identity. So I actually often call that representation 1.
Does that always correspond to the conjugate class of the identity?
The thing is, what does correspond to mean? No, I mean, I'm not trying to be too uptight, but there's not an obvious bijection, right? I mean, we get that there is some bijection, but there's not, in general, a nice one. It's an annoying part of life. There's not a natural way of parameterizing the representations in terms of the conjugate classes, or at least not always. So, great question. Here, I guess there is, because conjugate classes are elements of anything. Right. So I will later call this thing 1, or maybe 1 sub E, or actually maybe 1 sub G. I guess E is fixed, so it's the identity representation for G. So G can have other 1-dimensional representations. For example, this has lots of 1-dimensional representations. One of them is the 1, corresponding to I equals 0, I guess. But it has lots of other 1-dimensional representations. And in fact, it's not hard to see that 1-dimensional representations correspond to 1-dimensional representations of the abelianization of G. So for example, if G is a simple group that's not abelian, then it won't have any but 1. Like the derived subgroup of G will be equal to G, and so it won't have any abelian quotients. Right? I mean, if I'm going to have a 1-dimensional representation, it will give me a subgroup as the image of E star, which is an abelian.
Do we always rule out the 0 representation? It's not
so the 0, it's not a representation because 0 is not invertible, right? So it's a confusing issue for me and for others sometimes, because in the world of Lie groups, which is not quite what we have here, you have a group and then you have its Lie algebra, and so there's something that acts as 0, but that's the Lie algebra that does that. If those words mean something to you, that's good. If they don't, then tune me out. But I guess what that means is that the derivative of the trivial representation or the identity representation is the Lie algebra version has the elements of the Lie algebra acting as 0 instead of the elements of the group acting as the identity. So, but that's Okay. So those are the examples that I wanted to do, and I guess now I have to do a piece of algebra. Ouch. So given a subgroup H of G and the representation W of H, and I want a row for it. I could write rho sub W if you like. There's an induced representation of G. So let me pause for just a second. This thing is induced from the trivial representation of the identity group up to SN. Okay. So now I will cringe just because the right language for saying this is to look at.
Don't you mean an induced representation of H?
I start with a representation of H and then I build one out of it for G. So I build a representation of G in some sense. So here I'm going to pull you a little bit because it will play a huge role, but I won't be actually proving things. So if you're interested in unpacking all this, the spring awaits. So I can build something that I will call EG, or maybe I'll put square brackets. No, I guess I'll just write it as EG. So this is something called the group algebra. So what it is, I can think of it as E-valued functions on G, so not just class functions, but E-valued functions. Or I can think about it as just formal E-linear combinations of elements of G, and is an algebra. Because the multiplication in G tells me how I multiply things, and I just add as if it were a vector space and G were the bases. And I have also PH, similarly an algebra. And the important property of this is that W is an EH module. So a module over a ring is something that maybe you got had perpetrated on. There's the word I'm looking for. Perpetrated on you in the first year algebra class. So it's sort of like a vector space, only you let the scalars be more general, and here the scalars are maybe even not commutative. But at any rate, I have things in here that I'm permitted to multiply by elements of this ring. I get more things in here. And then I can form, gasp. I told you there was some reason for the tensor product to exist. So this is an EH module. EG is surely an EH module because H is inside G, and I just formed this tensor product. And that is the induced representation. Ugh. Anyway, no, it's nice, but it's not so nice for a talk like this because I don't want to get sucked into the details of it. So I will write this as NHGW, and then I'll just tell you that the main thing that we should notice is that the dimension as an E vector space, so this is what I would convince you of. I'm not going to write anything about it, but it's the dimension of W surely and the index of G and H. So what does that boil down to? It boils down to the fact that, right, in module language, let's see, that this, if I pick a system of coset representatives for H and G, those things give me a basis for EG as an EH module. So it's a free EH module, and I get a basis by taking a system of coset representatives. So there's me counting the system over coset representatives. That's the index of G and H. So that's technical. So I won't actually apply it, mainly apply when W is 1 sub H in the future. Yes?
But inequality even hold when H is not a finite index?
So all my groups are finite. Yes?
How much do we know, like, if there's a subgroup of H, okay? If I induce from K to G, or from K to H and then to G?
So induction is transitive because tensor product is transitive. So that's a great question. And that is one of the main reasons. So you can get around this. I could give you a definition that doesn't mention tensor product. And then you could prove that it's transitive, but you get it for free, and you get lots of other properties for free if you understand it in terms of tensor product. And anyway, it'll take me 10 minutes to say it, so I'm not going to torture you. I'm going to say this and probably with lots of eyes glazed over, and that's fine. So it's this thing that you get by some piece of algebra, but it, and I didn't know, you could state some universal property that it satisfies if you like, but at any rate, I mean, if all you take home from it right now is that I build some slightly bigger representation from G from a representation of H, then that's sort of what I wanted to tell you. That's some technical algebraic definition, but it is a problem. So okay, so that's my crash course on more than half my time on representations. So now, what else is in the title of my talk? Finite groups of Lie type. Oh my God. so here is the propaganda line. So somebody, actually a lot of people, proved a classification theorem for what are the finite simple groups. And that classification theorem said, oh, those include Z mod P, or prime numbers P, because those are cyclic groups, and P's prime, so there's no room by Lagrange's theorem for there to be any subgroups. And then there's the alternating groups. You've all seen the proof that AN is simple for n greater than or equal to 5, or something like that. And then there are some weirdos, aka sporadic groups. I think there are 26 of them or something, about which I know nothing. Anything that you tell me that is new to me. And then there are groups that come from matrix groups over finite fields. And those groups are called finite groups of Lie type. And I don't know whether they have a good reason to be that. I mean, they're just finite groups, and if you don't know anything about finite fields, they're still there, right? It's not, those are the groups, but it's a way of describing them, and it gives you a uniform description of most, or a lot of, I don't know, a lot of finite simple groups, all but the alternating groups. So, and finitely many weirdos. So there's a finite number of exceptions, and then there's a bunch of alternating groups, and then there's the simple groups of Lie type. Yes.
So I don't think you're going to come back to this. So you described two of the simple representations for SN.
Yes.
What are the other dimensions? Or is it not easy to describe?
Not easy to say what the dimensions are. So in SN, you have a pretty picture, which is why I paused a while ago when you asked your question, which was a great question. In SN, you could describe conjugacy classes by partitions. Right? You give me a set of numbers that add up to n, and then I'll say, oh, well, I want to have a lambda 1 cycle, and a lambda 2 cycle, and a lambda 3 cycle, and then the lambda i's add up to n, and that specifies a conjugacy class. And it turns out that you can describe the simple representations using partitions. It's just that the construction of the simple representations is somewhat ad hoc. You do this, some kind of big induction sort of game, and you take things apart and you prove that there's a unique part that has this property, and then you find the thing that you want. But on the other hand, there is sort of the same parameterizing data, so you could speak of the conjugacy class corresponding to the partition lambda and the simple representation corresponding to lambda, so at least that's somewhat satisfying, more than for a general random group. But I don't know, and I probably should know, I can never remember. One of the partitions is n, and one of the partitions is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. And I can't remember. I guess it depends on how you normalize things. One of those two corresponds to the trivial module, and one of them corresponds to the sign representation. So that takes the sign of the thing that the alternating group is the kernel of. So those two I know. Those two have dimension 1, and outside of that, I actually forget what partition this corresponds to off the top of my head. But in general, I think there are formulas. I'm sure there are formulas, but they're not pretty or easy to. Well, maybe they are pretty. They're not easy for me to remember. How's that?
Is there a operator reason why? Is there a bound on the dimension of the vector space for in terms of the order of the group?
Yes. Stuff. So the sum over the simple G representations of the lambda, a row of the squared is, and the square is a little bit odd. It comes from, I'm not sure how to explain it. The best way to think about it is here. So it turns out that this algebra is an algebra with a property called semi-simple, which actually means that it's a direct product of matrix algebras. And And the size of those matrices, so full matrix algebras, the ni by ni matrices over E. And ni is then the dimension of some vi. And then it's obvious that to get the dimension of the product, I add up the dimensions of the pieces, and this is me adding up the dimensions of the pieces. So it's a fact about this kind of algebra, but it's a good fact, and yeah, so it doesn't get me so big. It certainly can't be any bigger than the order of G. You actually have to add up to the order of G, and not only them adding up, but their squares adding up. Question? So, so maybe what I'm going to do is tell you one finite group of the type, and that will be G will be GLNFQ. Maybe I'll do it this way. So we'll just explain everything in terms of this group. So that is the matrix, right? So what is FQ? It's the unique finite field of order Q. So Q will be some power of a prime number P. And hopefully your Math 215-16 instructor proved that there's a unique field of that order for all powers Q of a prime. And so I get a field, and I can look at the matrix group, and this group has some order that I forgot to remind myself of the formula, but it's finite. It's a finite group, so we have finitely many coefficients to put in each place, and it's not all that close to simple, of course. I mean, it has a center, right? I can take the diagonal matrices, so really probably I should look at SLN, the special linear group. That's still not simple. I have to divide by a group of order n in general. Okay. So it's sort of quibbling. It's, most of it constitutes one of the simple groups that I was mumbling about, and I'm not going to worry about the details of how you get rid of the extra stuff. So, as my professor used to say, it's the law of conservation of dinky stuff. If you get rid of it here, it appears somewhere else. So, not worth losing sleep over that, but I want to realize that if K, so there's some reason that I called it's FQ bar, gasp. Then G, oh no, can't believe I wrote that down. G is, no, I wasn't supposed to do that. Then GLNFQ is the group of points, group of FQ points, so this is fancy terminology that I'll mumble about, of a linear algebraic group GLNK. So you're not probably persuaded, but what do I mean by this? This is an algebraic closure, so it's an algebraically closed field, and matrix groups over algebraically closed fields defined by polynomial equations have some nice properties. This is what I study. Linear algebraic groups. They're something like geometry. Here it's geometry characteristic P, but algebraic geometry doesn't see so much of that. I don't have to. There's a rich theory of groups like that, but I'm basically suppressing. I'm only talking about GLN. But so what do I mean by the group of points? In fact, there exists a so-called Frobenius map from GLNK to GLNK that does what? It takes Aij to, I'll take that to Aij to qth power. So taking qth power is an automorphism of this field, and it also happens to give me a regular map of varieties. I mean, it's obviously polynomial in the coordinates. So it's a nice map. I'll call this Frobenius map F, which is why we write E for the field. So and then the group GLNFQ can be productively thought of as somehow the fixed points of F, the things that are mapped by F to themselves. Right? This is Galois theory. So if I want to find the things that have coordinates in FQ, I should look at things like this that don't change when I apply capital F to them.
Do you mean that G is GLN and Q F?
So I don't mean this is G and this I mean is G. So G is the upstairs thing, and GF is the downstairs thing. That's why I was cringing a while ago. I didn't mean to write that. So, right. So Am I supposed to let you go at 1? I guess I am. So I will try to say what I want to say. So B will be a Borel subgroup gasp. What does that mean? So in this case, it means that it is the full upper triangular group. So the only condition that I impose is that the matrix entries below the diagonal are 0. And here is the magic: is that G mod B embeds in a product gasp I equal 1 to the dimension. No, it's in of the Grassmannian of I-dimensional subspaces of N. Why is that? Well, B is the stabilizer, since B is the stabilizer of a full flag in K to the N. So it's a flag in K to the N is a choice of a subspace of dimension 1 contained in a subspace of dimension 2 contained in a subspace of dimension 3, and so on. So in fact, the group GON is obviously transitive on flags, and B is exactly the stabilizer of them, and flags I can think of as being inside here. So why do I say it that way? These are so-called projective varieties. So the Grassmann variety I can embed in some projective space, which is the algebraic geometric version of being compact. So it's what you want. Somehow it's a compact space is like being a compact, complex manifold. So Brinley space. So this is projective, and then in general, a parabolic subgroup is a subgroup containing, sloppy B. So this is a Borel subgroup. Any Borel subgroup is a minimal one for which G mod B is a projective variety. So for example, this one, but it's a theorem, part of the structure theory of groups like this that says Borel subgroups are all conjugate. And in fact, there exists 2 to the n minus 1 parabolic subgroups containing a fixed B. So what's maybe another example of a parabolic subgroup would be the stabilizer of just a single vector. So for that parabolic subgroup, G mod P would be equal to the full projective space. So I didn't tell you what P is, but the stabilizer of a single vector because G is transitive on lines. So right. So this brings up lots of things that you will see if you take a course in algebraic geometry. This sort of Grassmann projective varieties are nice, and they characterize what we mean by parabolic subgroups. This is all said without mentioning FQ. So what I have to do, 4.5 minutes, is tell you that you can choose B such that FB is equal to B. So it's sort of defined over the ground field. The Frobenius map maps B to itself. I guess that's obvious. For this B, all I did was take powers of the matrix entries, so they didn't move the matrix entries around. There are other B's where it would be much crazier. So this B happens to be friendly for that Frobenius. So that's fine. And then the same is true for all P containing B. So any parabolic subgroup containing such a friendly B that's defined over the finite field is also defined over the finite field. And so I get, in this way, some nice subgroups. The fixed points of the Borel containing the fixed points of the parabolic subgroups containing G. So now I get to write down the horrible definition and tell you, so this is the Steinberg representation. I'm supposed to have another few minutes to justify this. But the Steinberg representation, what I do is that I sum over all parabolic subgroups, the 2 to the n of them, that contain my fixed B, and then I take the minus 1 to some sign that I'm going to be vague about in just a second. It has to alternate based on some dimension, and then I take the n. GF. trivial representation. So I take some induced representation construction from PFs. So parabolic subgroups of GL and FQ. So those actually, it's not so hard to describe them. I can draw block matrices, put zeros down here, and stars up here. That's a typical P. So it's something that has to contain B, and it will have as a quotient a product of GLNs. And then it'll have some normal P subgroup, so a solvable, or even a nilpotent P subgroup. So in some sense, PF looks like a product of the kind of groups that we started off with, extending to some weirdo P subgroup. And I formed these induced representations, and I can count the dimensions of these. Those are just the index of GF and PF, right? Because this has dimension 1, and I have some formula. And then I make them alternate, and I'm not going to make you put up with me specifying how that sign goes. It has something to do with, if P were bigger than B but didn't contain anything else, then I would assign the sign -1, and then if I had a P that was bigger than that didn't contain anything else in the middle, I would make it plus again, and it goes back and forth based on the dimension of P or S. Then you're supposed to say, well, what does the sign mean? These are representations. So actually, I guess I mean this in the sense of a generalized representation. I have to think in the Grothendieck group of all representations, where I get to put coefficients, but then it turns out to be a theorem that the Steinberg representation is a simple representation of GF. So the way to think about it, or the way to prove it, and I was going to say a little bit more, but I'm not going to make you sit do it, is that somehow too, the general linear group, there's associated, it's a Weil group, whatever I mean by that, but in this case it's the symmetric group, so the permutation matrices. It's the normalizer of the diagonal group, mod the diagonal group. And Weil groups are Coxeter groups, and their job in life, in this role, this sort of business, is to do bookkeeping for you. So they keep track of a lot of the geometry and numerical stuff, and somehow you can turn the question of computing this inner product, or the inner product for the corresponding characters, into a question for the symmetric group. And once you do that, you can actually compute it because it's finite. So that's how the game goes. And you find out that this is 1. And what that really means is that Steinberg is either an irreducible representation, or maybe it's negative of an irreducible representation, and you have to rule that last fact out. So finally, I'm going to tell you what it tells you, and then I'll shut up. So it turns out that well, its value at the character of Steinberg at 1 is, in this case, it's p to the n times n minus 1 over 2. What does that mean? This simple representation's dimension is, in general, a pretty big power of the prime number that you sorry, it's q, not p. So it's a power of q. So the dimension is pretty big. Q is big. And let me just write down, or let me check, just so I can just say it and let you go. So the theorem that I wanted to describe is that the number of unipotent elements, let's see whether I can tell you what a unipotent element in GL and FQ, I guess you could count those, but it's equal to take take the order of this and take the p part of it, right? So the order is a product of a number that's relatively prime to p, and then you can take the p part of that number and then you square it. And you prove this, prove using Steinberg character. It's actually true for much more generality. I guess you could probably prove it directly for GL and FQ. So what's a unipotent element? A unipotent element is something like, it's an upper triangular matrix that has 1s on the diagonal, or it's conjugate to an upper triangular matrix. It's one that has 1s on the diagonal. So counting upper triangular matrices that have 1s on the diagonal is not hard. That's the number of things in the CELO subgroup of B, if you like, or B upper F. But in general, the number of unipotent elements is not something that's obvious how to count. But on the other hand, you can get factual information about the value of this trace function on elements. And what turns out to be true is that this trace function vanishes on any element that's not diagonalizable, that's not semi-simple, which is a remarkable property, especially given the complexity of its definition. But, and that vanishing lets you get at this fairly quickly. I'm just going to give you just. But anyway, so the thing that I wanted to argue is that somehow representations can then give you back information about groups that you might care about. So for example, knowing about different sorts of matrices and counting types when it's not easy to count. I mean, Q is a parameter here. It's big. Okay, anyway.